Hi, let's continue with some more problems from the harmonic oscillator. The first problem is to find the product of uncertainties delta x delta p in the nth energy eigenstate. Alright, so the given, if the state of the system is an energy eigenstate, let's say the nth energy eigenstate, what is the general expression for the product of uncertainties? Okay. So in order to find the product of uncertainties, in order to find the uncertainties, you need expectation value of x, expectation value of x square, expectation value of p, and expectation value of p square, because we know that the uncertainty was defined in this way: delta x equal to square of the expectation value of the square minus square of the expectation value. Right, it's the expectation value of the square minus square of the expectation value. This is the definition for uncertainty in an operator in a given state. Okay, so we find these expectation values by using the given state. All right, here the state is given as the nth energy eigenstate. So let's first find expectation value of x. Okay. So we are finding expectation value of x in the state n. So it's simply n x cap n. We know that it's actually bra n x cap ket n. Okay, it's this combination. This is the expectation value, right? And what we do now is we substitute for x cap in terms of a and a dagger. Right? So we know that x cap is equal to square root of h cross by 2 m omega a dagger plus a. You have seen this thing, right? It's square root of h cross by 2 m omega a dagger plus a. So we just substitute it here and we see immediately that this has to be 0. Why? Because a acting on this system n will take it to another state n minus 1. Alright, and this n minus 1 scalar product with n is 0. Why? Because they are orthonormal states. Alright, they are orthonormal states. Similarly for a dagger acting on n will take it to another state n plus 1, ket n plus 1, and the bracket of n and n plus 1 is 0 because of orthonormality. Alright, this is the reason why we say that if you are finding an expectation value, alright, if you are trying to do an expectation value problem, the terms in which a and a dagger are not balanced, right? If there are terms in which a and a dagger appear an odd number of times, okay, different number of times, then the contribution from those terms will be 0. Right? For example, if you had a term like a dagger, there would be a non-zero, there can be a non-zero contribution. Okay, this is when we are finding the expectation value, and in this case we see that there are both terms are unbalanced in terms of a dagger and a. In this term there is only one a dagger, there is no a. In this term there is one a and there is no a dagger. Okay, so this is 0. Similarly, we will see that expectation value of p is also 0 because the definition, the expression for p in terms of a dagger and a is simply this is I square root of mh cross omega by 2 a dagger minus a. Okay, these two are relations that you have to remember because x cap in terms of a dagger and a, also p cap in terms of a dagger and a. Okay, so this is also 0 for the same reason, right? Now we can go on to find expectation value of x square. Right? So we just substitute x square in here. It's h cross by 2 m omega a square, a dagger a dagger. Okay, immediately we know that these two terms will give you 0 contribution. Why? Because there is just a square twice acting on n. Okay, that will take it to a state n minus 2 with some normalization factor, and n minus 2 with n will be 0 because of orthonormality. Alright, so these two terms will immediately give you 0, and we know that a dagger a is known as the number operator. Acting on n, it just gives you the number n. Okay, similarly a dagger is also n is also an eigen function of a dagger. It's also an eigenvector of a dagger with eigenvalue n plus 1. We have seen this. Okay, so this gives n plus 1. So it's actually 2n plus 1 with this constant. Okay, so it's easy to calculate. H cross by 2 m omega 2n plus 1 is the expectation value of x square in the nth energy eigenstate. Similarly, let's find it for p square. You can complete this thing. Again, there are only two non-zero terms. This minus will get cancelled with this minus, and you have got again mh cross omega by 2n plus 1. Okay, what we need to find is the uncertainties. In order to find the uncertainties, we use this relation expectation value of the square minus square of the expectation value. Alright, but this term is anyway 0, so it's simply square root of the first term alone, and it's this. Right? Similarly for delta p. right? And the product of uncertainties we see is delta x delta p is n plus half h cross, right? It's n plus half h cross, and clearly we see that this obeys the Heisenberg uncertainty relation because delta x delta p is greater than or equal to h cross divided by 2. Okay, all right. So, and now we could, so this is consistent with Heisenberg uncertainty relation, all right. Now, what happens if n equal to 0? What happens if n equal to 0? If you are talking about the product of uncertainties in the ground state, right, in the ground state of the harmonic oscillator, then you just put n equal to 0 and you see that delta x delta p is equal to h cross by 2. Right? The Heisenberg uncertainty relation says that it has to be less than or equal to h cross by 2. So, in the ground state, right, the ground state of the harmonic oscillator has this nice property. It's that the product of uncertainties in the ground state, okay, corresponding to the ground state, has the minimum value, right? It has the minimum value. So, we can say that the ground state of the harmonic oscillator is a minimum uncertainty state, right? The ground state of the harmonic oscillator is a minimum uncertainty state. Going on to the next problem, calculate the expectation value of the operator x raised to 4 in the n representation with respect to state n, ket n. So, we are supposed to find this thing, right? Now, use this result to calculate the energy En for a particle whose Hamiltonian is, here is given a Hamiltonian for which the first part is exactly the harmonic oscillator Hamiltonian, right? The second part, there is an extra part here, that's lambda x raised to 4. So, we are supposed to find this expectation value and then go on to find the energy eigenvalue for this, okay? All right. So, how do we do this? So, we are asked to find it in the energy eigenstate, all right, with respect to state n. How do we do this, all right? So, there is a brute force way and a smart way of doing it. The brute force way would be to write down x raised to 4 in terms of a and a dagger, right? For this, we have to be careful. We have to find a plus a dagger square and then multiply a plus a dagger square with another a plus a dagger square. Take care with the ordering of the operators and then just do this, all right, using the relations that we already know. Okay, that can be done, all right. That's a brute force method. I ask you to try this method, all right. It's not very difficult. We just have to be a bit careful. You will see that so many terms will go to 0 because a and a dagger appear a different number of times in certain expressions. So, you can immediately neglect them and then go on to do it. It's not too difficult, but it takes a little bit more time. Right. So, I want you to try this brute force method because it gives you some practice. All right. Now, what we do here is slightly different. What we do here is that we will make use of the fact that this n, all right, this states n, they form a complete set. All right. It's an orthonormal basis. It's an orthonormal basis. This is an orthonormal basis. All right. This means that it obeys a completeness relation of this form. Right. So, if you take all these states and take this combination, add up all these combinations and then you should get the identity operator. This is known as the completeness relation, all right. This means that you can expand any vector in this state in this basis, all right. Any vector can be expanded in this particular basis, okay. So, this is what we will do, and now what we do here is that we will write down this n x raised to 4 n, as we will write it as n x square n, all right, and in between here we will introduce the identity, all right, like that, okay. Now, we have already used n here as a free index, okay. So, we have to use a different for the summation purpose. So, we will use it as m, all right. So, what we do here is actually we will write this as summation m equal to 0 to infinity, okay, n is there and then x square, here we put this identity thing, okay, all right, where summation m equal to 0 to infinity, m is the identity operator, all right. These are the energy eigenstates or the occupation number states, eigenstates, all right. Okay, so, we can introduce this identity operator in here. This is a trick that is useful many times. Alright, so just be careful. Here n is already used as a free index. Alright, we have used it. So we have to use some other index for the summation. Alright, otherwise we get it all wrong. That's the only thing we have to be careful here. So that's what we do here. We write n x raised to 4n as n x square m, m x square n summed from 0 to infinity over m. Alright, now we know that this x square is a Hermitian operator. We know that the x square here is a Hermitian operator. This means that this n x square m is actually the complex conjugate of m x square n and vice versa. Am I right? This n x square m is a complex conjugate of m x square n. Alright? Why? Because we have this relation. If you have something like phi I, alright, a phi j. Okay? Let's say psi, just phi and psi. Alright, phi. We know that there's this relation a dagger phi. Okay, so if we switch these things, you get an extra a dagger. Right, but when we deal with Hermitian operators, there's a star here. Right, this is basically the definition for self-adjoint or complex Hermitian conjugate of an operator. But operators which are Hermitian, a dagger is equal to a, so we can simply write as psi a phi star. Alright, so if you don't remember this, please go get back to the definition for Hermitian conjugate and how we define the Hermitian operator. Okay, so this means that what comes here is the complex conjugate of this and vice versa. So what we have here actually is the modulus square of m x square n. Right, now our job is just to find m x square n. Alright, it's called as the matrix element of x square between the states m and n. Alright, this is known as the mnth matrix element of x square, or we can say it's the matrix element of x square in between the states m and n. Okay, so now we know x square already. We have written down x square in terms of a and a dagger. It's h cross by 2m omega a square plus a dagger square plus a dagger plus a dagger a. Now we have to be a bit careful because this m takes all possible values. Right? This m takes all possible values. It's not the same thing appearing on both sides. Right? We are not finding an expectation value. We are finding this matrix element, and there's a summation, there's an infinite summation, which means that all possible values of m should appear here. Right? So let's look at each term separately. Right? Let's look at each term separately. First we put, so when you do this thing, you just, this h cross by 2 m omega is there. Let's just take this a square part. Okay, what happens in this whole thing? You can write it as a square n. Right? First let's find this. What's going on with this? We know that the summation m equal to 0 to infinity. We'll find each term separately. Okay, what happens when a square acts on n? We can write it as m equal to 0 to infinity m. All right, we first act one of the a. We keep one a because it's a square. You act one a on it, and that will give you square root of n minus 1. Am I right? So this is a number. You can pull it out. Square root of n summation m equal to 0 to infinity m a n minus 1. We know what happens when a acts on n minus 1. It becomes n minus 2. So this is square root of n summation m equal to 0 to infinity m square root of n minus 1, and then what you have here is n minus 2. Okay, so this is simply square root of n into n minus 1. Okay, m n minus 2. All right, and then don't forget we have the summation over m equal to 0 to infinity, which means that you are taking all possible values for this m. All right, so when you take all possible values for this m, all the terms will be 0. All right, because of orthonormality, except when this m is equal to n minus 2. When m equal to n minus 2, all other terms will be 0. Right, so there's only one contribution from here when m is equal to n minus 2. Right, so that means that the answer here is square n into n minus 1, square root of n into n minus 1. Okay, Alright, so that's in the same way we can find for a dagger square, a dagger, a dagger, a. Alright, so we write it down in this form. First, this thing. Alright, so another way of saying is this. So the non-zero terms in mx square n. Alright, the non-zero terms for mx square n, or the terms that survive. Alright, this is the term that we are talking about. Alright, when you do n minus 2 x square n, that a dagger square term will be non-zero. Alright, so that's what we have here. So this is h cross by 2 m omega square root of n into n minus 1. Alright, that's exactly what we wrote here. Square root of n minus n into n minus 1. We are just finding m a square n. Okay, so the m a square n term gives square root of n into n minus 1. Alright, in the same way we can find other terms. You can see, okay, I want you to work it out. You know the relations. Alright, please go through it. The other term, when if you do a dagger square, okay, you can do exactly the same thing, and you will see that the non-zero term appears for n plus 2. Alright, when you do n plus 2 here in the whole summation, when m equal to n plus 2, there is a non-zero term, and the factor appearing square root of n plus 1 multiplied by n plus 2. Why? Because we know that a dagger acting on n is written as n plus 1, square root of n plus 1, n plus 1. Okay, that's once. If a dagger acts twice, this becomes square root of n plus 1 multiplied by n plus 2, and what appears here is square root of, get n plus 2. Okay, this is a dagger acting on twice. So if when m reaches n plus 2, you will get a non-zero value. All other values will be 0. Right? That's what we have here. Similarly, for there are also non-zero terms when both these are n is equal to m. Okay, that corresponds to terms where the a and a dagger appear an equal number of times. All right, a dagger a plus a dagger. Okay, and we already know this thing. When a dagger a plus a dagger comes between this, we already know that it is a 2n plus 1. Okay, and then we have left out this h cross by 2m omega. When you add that, you get h cross by 2m omega 2n plus 1, h cross by 2m omega square root of n into n minus 1, and h cross by 2m omega square root of n plus 1 into n plus 2. All right, in this whole summation, in this whole infinite summation, these are the only terms that will survive. All right, these are the only terms that will survive because of the orthonormality relations. Okay, I hope that's clear. Right, so we'll say that these are the only terms that will survive. So now we already found here that what we wanted here is sum over m equal to 0 to infinity and the square, the sum of squares. Okay, so you square all these terms and add, square all these terms and add. Okay, because these correspond to each of these correspond to different value of m. Right, in this whole summation, these are non-zero values, and each of these correspond to a different value of m. So you sum over all these things, you get nx square n whole square plus n minus 2 x square n whole square plus n plus 2 x square n modulus square. Okay, not whole square, it's modulus square. Okay, I hope this is clear. What we have done is we have taken this infinite summation, and we have realized that in this infinite sum, these are the only terms that will give you a non-zero value. All other terms will go to 0, and this we have already found. Just substitute it here, and then the final answer simplifies to h cross square divided by 4m square omega square 6n square plus 6n plus 3. Okay. So that's fine. We have found the expectation value for, not expectation value, yeah, we have found the expectation value for x raised to 4. Alright, that's the answer. Alright, now we have got this Hamiltonian. The Hamiltonian here can be expressed in terms of the harmonic oscillator. The first part I said was the harmonic oscillator term, and then there's an extra term. Right. Now this leads us, we can write the particle energy in this form. Actually, we are finding the expectation value of the energy here. Okay, we have got NHN, the harmonic oscillator part. This we already know. And then we have got lambda n x raised to 4n. This we have already found out. Alright. Now this part is h cross omega n plus half minus lambda h cross square by 4m omega m square omega square 6n square plus 6n plus 3. Right now, if you want, you can simplify that further or leave it at that, and that would be the answer. Right, such questions can be asked. Okay. Now, you might be wondering, right, if we were asked to find the energy eigenvalue, but what we have found here is the expectation value. Am I right? What we were asked to find was the energy eigenvalue. Right, but what we have found here is the expectation value. Right, if you are concerned about that, you should remember that if you take the expectation value between eigenstates, all right, in an eigenstate of an operator, then you get exactly the eigenvalue. All right, see, for example, suppose we have got this A acting on phi I is equal to AI, phi I. All right, so this is the eigenvalue equation. Now, what if you find the expectation value phi I A phi I? What do you get? So, this is phi I AI phi I, and then you can pull this, there's no summation here, right? There's no summation here. So, you pull this AI outside, phi I, which is equal to 1. Sorry, which is equal to AI. This is equal to 1 because of orthonormality. Okay, that's exactly what we have here by taking the expectation value between the in the eigenstates. All right, if you take the expectation value in its own eigenstates, all right, where the state is the operator's own eigenstate, then what you get is basically the eigenvalue. Okay, so that's the reason why we get the answer for eigenvalue here. Okay, I hope that's clear. Moving on to another problem. Consider a particle of mass m and charge q moving under the influence of one-dimensional harmonic oscillator potential. All right. Assume it is placed in a constant electric field epsilon. The Hamiltonian of this particle is therefore given by, we have got the Hamiltonian. The Hamiltonian is given. All right. The Hamiltonian is given here. Derive the energy expression and the wave function for the nth excited state. Here we are supposed to find the energy and the wave function for the nth excited state. All right. So, we have got the normal harmonic oscillator term and then an additional term, all right. Now, just by looking at it, all right, here you have got x multiplied by some factor, and here you have got x square. All right. So, just by looking at this form, we see that this is something like of the form a square minus ab. Right, this is a square and then minus ab. Right, we have to make a little bit rearrangement, but this is like a square minus ab, which means that we can express it as a complete square. How do we do that? We know that a square minus ab is actually a minus b whole square minus b square, because this would be a square plus b square minus 2ab. All right, so we can say a square minus 2ab here. Sorry, there's a 2 here. All right, it's a square minus 2ab. Okay, so a square minus 2ab can be written as a minus b whole square minus b square. Okay, so that's this, we can bring it to this form and then complete the square, and then things will be simpler, as we will see. So, what we do here is that we take these terms half m omega square x square minus q epsilon x cap. All right. So, this we want to isolate this x square term. So, we pull this half m omega square outside. We pull this half m omega square outside, and what we have is x square minus 2q epsilon x divided by m omega square. Okay, I hope this is fine. I have just pulled this half m omega square. Now, this is of the form that we like. This is exactly of the form a square minus 2ab. All right, where a, in place of a we have x. Okay, in place of a we have x, and in place of 2ab, you have got 2q epsilon x divided by m omega square. Okay, so this means that b would be, a is x and b, so 2 is gone. So, b would be simply q by m omega square, q divided by m omega square. That's also epsilon. So, it's q epsilon divided by m omega square. So, we can write it as a minus b whole square minus b square. Okay, that's a minus b whole square minus b square. Okay, we have done exactly that. Okay, so we have if we exclude this 2x cap from here, what remains is the b part, right? Because this looks like a 2ab part. Okay. Now, this is nice because we have got a complete square minus a constant here, all right, minus a constant here. There is no x or p in this. Now, this makes things simpler. That's exactly why we do this, right? So, we are writing it as the given term, We are combining it in a form which is a complete square minus a constant term. Okay, so that makes things easier. You will see how. So this is now half m omega square x minus q epsilon m omega square whole square minus q square epsilon square by 2m omega square. Okay, I've just multiplied this half m omega square inside. Now what is this? This is exactly the harmonic oscillator potential with the change, all right? If we take a coordinate where y is equal to x cap minus q epsilon by m omega square, all right? If instead of x we put x minus q epsilon by m omega square, this is exactly the harmonic oscillator potential, all right? So what we are doing here is that we are just shifting the coordinate system a little bit. We are just shifting the coordinate system to the right by a factor q epsilon by m omega square, all right? So that means that this is just a translation, or we can say are translating the system towards the left by a factor q epsilon by m omega square. All right, this is a simple translation and it doesn't change the properties of the system. This simple translation, we are using a new coordinate system which is translated by a constant amount. That's all. Okay, so we make this we make this variable change. We say x minus q epsilon is your new variable. Sorry, x minus q epsilon by m omega square is your new variable y. Okay, so now the Hamiltonian becomes half 1 by 2m p square plus half m omega square y square, and then there's a constant term here. Right, now this is our familiar harmonic oscillator Hamiltonian, and the eigenvalue corresponding to this term we already know. It will be En is equal to n plus half h cross omega. This we had already found. It's exactly of the same form. Okay, if you shift the coordinate system by a small factor or by any factor, it does not change the results. All right, it's known as translation invariance, etc. It's known as a translation invariance. Right. So what we have here is an extra term, and if you take, for example, as just before, let's just take the expectation value in the energy eigenstate. Then we know that we get the energy eigenvalue, just as I said before. Right. So corresponding to this part, you will get En, and this is the expectation value of a constant. So that just follows. So En minus q square epsilon square divided by 2m omega square. I hope this is clear. Right. Just repeat. I will just repeat. So here, this is the harmonic oscillator potential. I will write it as HO, right? And this is some interaction term. So if you do this thing, NHN, what you get is NHON minus NQ square epsilon square by 2m omega square n. Right, now this is just a number, it can be pulled out. So this is En, we know that, minus q square epsilon square divided by 2ma square. Okay, so that's the answer we have here. En is h cross omega n plus half minus q square epsilon square divided by 2m omega square. Alright, now what's the wave function? The wave function is fine. Alright, you just make the change of variable in the wave function also, that's all. Right, we can write sine of y. We already know what sine of y. It is this, right? If it's a y here instead of x, you get exactly the same thing. Only that instead of x, you have to put a y there, right? So that's the nth, nth energy eigenfunction. Right? Now, such problems have been asked in previous exam. Okay. Right. So the thing that was asked was. So such questions have been asked in the previous system. Usually they ask a harmonic oscillator thing minus something like, let's say lambda x, something like h harmonic oscillator minus lambda x. So then this is exactly what you have to do. All right. In this place, we have got, yeah, all right, minus lambda x. Okay, that question, so it could be 2 lambda x, whatever, lambda x, all right. Then if such questions are asked, if you have something like a harmonic oscillator Hamiltonian minus or plus something like a lambda x, all right, then immediately you complete the square and then you can write it as a total square minus a constant term, right? Then the result is easy. Okay, this question has been asked in previous net exams. All right, here's another problem. Consider a system whose wave function at time t equal to 0 is given by psi of x comma 0 is this is the wave function. All right, this is the state of the system. You see that it's in a superposed state. Right. And what are these phi n of x? These are the wave function of the nth excited state for a harmonic oscillator of energy En. All right. So this is exactly a superposition of energy eigenstates. Okay, you can write it in a more familiar form if you want. This is actually, this means psi of x0 is 5 by square root of 50 0 plus 4 by square root of 50 1 plus 3 by square root of 50 and 2. This is the state that's given. All right, it's written in a slightly different form, that's all. Okay, now what are we to find? Find the average energy of the system. Find the average energy of the system. All right, so we know what's the energy when. So we first check. All right, first thing we check is whether the wave function is normalized. All right, we see that the wave function is indeed normalized, because you see if you square and add the coefficients, you see you get 25 plus 16 plus 9 divided by 50. Okay, so that's 50 by 50 and that's equal to 1. So it's a normalized wave function, which means that the coefficient, the modulus square of the coefficients can be taken as the probabilities, okay, for measuring certain energy values. All right. So there's one possible energy value is the one corresponding to n equal to 0. There's other one corresponding to n equal to 1, and there's another one corresponding to n equal to 2. Okay, for n equal to 0, so the probability to find the energy corresponding to n equal to 0 is modulus square of 5 by square root 50. Similarly, the probability for measuring an energy corresponding to n equal to 1 or E1 is simply 16 by 50. Similarly, the probability for finding an energy, if you make an energy measurement, the probability that you will get an energy E2 will be 9 by 50. Okay, this was one of the things that we saw in the postulates of quantum mechanics. That's how we do that. Right. Now find psi of x comma t at a later time t and the average value of the energy. Compare the result with the value obtained in A. All right. So we have to find the average value of the energy using the new state. Okay, state after a time t. Okay, then you have to find the expectation value of the operator in this state, in this given state. Okay, so let's look at the solution. The average energy, as I said, is 25 by 50, which is modulus C1 square. This square gives you the probability for measuring an energy E0. And what's E0? E0 is h cross omega by 2. It's because the eigenvalues are n plus half h cross omega. Okay. Similarly, it's modulus C2 square multiplied by E2, and this is plus modulus C3 square multiplied by E3. Right. So now we just simplify this, and I think the answer should be 59 by 50 h cross omega, but I want you to check whether this is correct. All right, if there's any mistake in the addition that I have done here. Okay, so that's how you find the expectation value. Now what about the state at a time t? We are given the state at some time 0. Right? We are asked to find the state at a time t. What's the state of the system at time t? Right. So this is easy because we know how each of the energy eigenstate evolves in time. We know exactly how each of the energy eigenstate evolves in time. Am I right? Because if you have an energy eigenstate, let's say if phi 0 is an energy eigenstate, let's say phi n is an energy eigenstate, we know that the time evolution is given by e raised to minus I e n t by h cross. Right? That's how the time evolution is given. Right? So we saw this in the time independent Schrodinger equation. There were two parts. There was a time dependent part and there was an energy eigenvalue equation. And if we combine them, we get the time evolution. All right? So the time evolution of an energy eigenfunction is quite simple. It comes in the form e raised to minus I e n t by h cross. Okay, you have to keep this in mind. Okay, so this helps us to do it. So it's this is the state at some time 0. So at some time t, you will have e raised to minus I0 t by h cross here, and e raised to minus I e1 t by h cross, and here e raised to minus I e2 t divided by h cross. Okay, that's the time evolution of each of the terms separately, and together that will give you the wave function at a later time. Okay, all right. That's what we have here. This is actually E0 divided by h cross. E0 is h cross omega, so h cross omega by h cross is simply omega. Okay, so that's why we have e raised to minus I sorry, it's half h cos omega, all right, minus I half omega t, all right. This is actually, this together is actually E0 divided by h cross. Okay. Similarly, what we have here is E1 divided by h cross, and this is E2 divided by h cross, because E2 is 5 by 2 h cross omega, so divided by h cross is 5 by 2 omega. All right. Now we are supposed to find the expectation value of the Hamiltonian or energy, the average energy, if this is the state. All right. Here we have to find the average energy if this is the state. Okay. Again, you can do the exact thing. You just take this as the coefficient. You take this as the expansion coefficient. All right. If you take this as the expansion coefficient, you get the, you can use exactly the same formula. You can use exactly the same formula as we did in the previous case. Yeah, this thing. All right. So this is, so it's, this is C1 and this is C2 and this is C3, right? So the average energy is modulus of C1 square E0 plus modulus of C2 square C1 square, sorry, modulus of, we can call it C0, C0 square E0, modulus of C1 square E1 plus modulus of C2 square E2. Right? You see that you will get exactly the previous value, because when you take the modulus square, these terms will get cancelled, all right? Because the modulus square of e raised to 5 by square root of 50 e raised to minus, just do this thing for you, modulus square, modulus C0, let's say C0, all right? Let's call this as C0, C1 and C2. Okay? Modulus C0 square, this is 5 by square root of 50, and then e raised to minus I 1 by 2 omega t multiplied by e raised to I 1 by 2 omega t, and these terms will get cancelled because you are multiplying the number with its own complex conjugate, so they will just go away. All right. So you see that the expectation value of energy does not change after some time, it remains the same. The expectation value of the energy remains exactly the same. Okay. All right, it happens because these are energy eigenstates. All right. What was the third part? Find the expectation value of the operator x cap with respect to the state psi of x comma t. Okay, so that's that I leave it to you as an exercise. We need to find, you take this as the state psi, you need to find, this is psi, okay, you need to find psi x psi. All right. So when you write down, you be careful when you write this psi, this is equal to, if this is psi, then the psi is equal to 5 by square root of 50 phi 0 e raised to I half omega t, etc. plus 4 by square root of 50 phi 1 e raised to this. These are kets, these are brass. Okay, the kets become brass and the numbers become their complex conjugate. All right. So you have to put it and then you have to take all possible combinations. All right. Before that, you can actually do this is, you can write it in terms of A and A dagger and maybe take out only the non-zero terms. Right. You can take out only the non-zero terms. All right. So there are non-zero terms because, for example, I'll just give you an example. If you do this, you will get a term, right? When you expand this, you will get a term of the form 5 by square root of 50 multiplied by phi 0. I'll write it in this form just to be clear. E raised to minus I 1 by 2 omega t. All right. This is number. You can take it outside, of course. It's plus. Okay. You get the complex conjugate. And then x cap. Let's look at one term in it, A. Okay. You have got a phi 0 here. So if phi 0 a phi 0 is 0, we know that, but phi 0 a phi 1 is not 0. All right. So this term will survive. All right. So this term will survive. So you have to be careful. There is a surviving term for a. All right. Phi 0 e raised to this term will survive because a acting on phi 1 will give you phi 0 multiplied by some normalization factor. In this case, that normalization factor is 1. Okay. So this term will actually survive. All right. Similarly, there is a term surviving for a dagger also. There is a term surviving for a dagger. For example, this this phi 1 a phi 0. For example, the term phi 1 A dagger phi 0, that will survive. Also phi 1 A dagger, sorry, phi 2 A dagger phi 1, this will also survive. Similarly, here there is one more term that's surviving, there is also the term. So, I will just give you the idea here. The terms that survive are phi 0 A phi 1, okay, and then you have got phi 1 A phi 2, this term will survive, alright. The other terms involving A will go to 0, alright, because of orthonormality. These are just the end states that we talked about. Okay. Now, there are also terms phi 1 A dagger phi 0, because A dagger acting on phi 0 will give you phi 1 and then you will get it. So, phi 2 A dagger phi 1 will also survive. Alright. These are the 4 terms that will survive, and then you take care of these constants, you multiply them properly, you will get the final answer. Okay. So, that is left as an exercise. I have actually practically given you all the steps here, but you try to do that. It is a good practice problem, right? You work a little bit with these kinds of things and you will be comfortable. Right. So, that is left as an exercise. There are 2 more exercises here. Calculate n x square m, right, it is an m here, and m x raised to 4n in the n representation, n and m are harmonic oscillator states. Right. So, you can either use a brute force method here or introduce what do you say, an identity operator in between as before. Alright, you will get the answer in terms of Kronecker deltas, something like delta n m minus 1, etc. Alright, or m minus 2. There will be terms involving delta n m minus 2. This means that the only non-zero term corresponds to n comma m minus 2, etc. Okay, and you will see that you can write the answer in terms of the Kronecker deltas. Alright, so please try this out. See whether we can write it in a nice and simple form. Now, the last exercise for you, it's just like the problem that we did earlier. If the state of a particle moving in a one-dimensional harmonic oscillator is given by, it's given as a superposition of energy eigenstates, where n represents the normalized nth energy eigenstate. Find the expectation values of the number operator n and of the Hamiltonian operator. All right. So, you find the expectation value of n and the Hamiltonian operator. Okay, that is rather simple. You just find psi n. Psi, you know how n acts on these states. Okay, so it is not difficult. Also, you find psi h psi. Okay, so this is easy because you will see that there are only a few non-zero terms because these are the eigen values. Okay, you can just do the whole thing if you want. All right, you can easily pick up the non-zero terms. Okay, so basically what you will do is do this thing 1 by square root of 17. Okay, 1 by square root of 17, 0 plus 3 by square root of 17 bra 1 minus 2 by square root of 17 bra 2 minus square root of 3 by 17 bra 3. Okay, and then you can sandwich the operator, whichever operator you are looking at, and then write the rest of the wave function right here. Right, and you will see that there are the cross terms will vanish because these are eigenvalues. All right, the cross terms will vanish. So the first non-zero term would be 1 by square root of 17 0 h 0. All right, then the 0 h1 will be 0, 0 h2 will be 0. Right, similarly 1 h1 and 2 h2, like that. All right, these are the non-zero terms. The same is the case for n also. Okay, because these are eigenvectors, these are common eigenvectors of both n and h. Okay, so I hope you can do these things just to get some practice. Such problems can be asked for the exam. Right, so with that we'll wind up this session, and we'll continue in the next class. Okay, thank you.